Imagine spending hours crafting the perfect embedded system code, meticulously writing every line, and then uploading it to your microcontroller. You hit the run button, expecting a flawless execution, but nothing happens, or worse, it behaves erratically. What went wrong? How do you even begin to fix it? Debugging is profoundly important during code flashing because it ensures the integrity, functionality, and reliability of your embedded system. Flashing code, which is the process of transferring your compiled program from your development environment to the microcontroller's non-volatile memory, is a critical step. And without effective debugging, any issue, no matter how small, can render your device useless or unsafe. The core reason debugging is so vital stems from the unique characteristics of embedded systems themselves. Unlike general-purpose computers with ample resources and user interfaces, microcontrollers often operate with limited memory, processing power, and without a dedicated screen for direct output. This means that errors, whether they are logical flaws in your code, incorrect hardware initializations, or timing issues, are not immediately obvious. The flashing process itself can sometimes introduce problems, such as incomplete transfers or corruption, making the debugging tools essential for verification. You are essentially working in a constrained environment where every instruction and every byte of memory matters. To effectively debug, you should first utilize the tools provided by your integrated development environment, or IDE. These often include a debugger that allows you to step through your code line by line, inspect variable values, and observe register states in real time as the code executes on the actual hardware. You can set breakpoints at specific lines of code where you suspect an issue might occur, pausing execution to examine the system's state. Another practical approach is to implement serial communication to output diagnostic messages. This lets your microcontroller send data back to your computer, providing insights into its internal workings, like confirming that a sensor is read correctly or a specific function is being called. A key concept to understand is the difference between simulation and on-chip debugging. While simulators can help catch many logical errors before flashing, they cannot perfectly replicate the real-world electrical characteristics and timing nuances of physical hardware. True debugging during flashing, often referred to as in-circuit debugging, directly interacts with the microcontroller while it is running. This allows you to observe how your code behaves under actual operating conditions, accounting for voltage fluctuations, electromagnetic interference, and precise timing dependencies that simulations simply cannot model with complete accuracy. Ultimately, embracing robust debugging practices transforms code flashing from a hopeful upload into a confident deployment. By actively checking, verifying, and refining your code after it resides on the microcontroller, you not only fix current problems but also gain a deeper understanding of your system's behavior. This iterative process of flashing and debugging builds reliable, efficient embedded systems, ensuring your carefully crafted code performs exactly as intended in the real world.